Somewhere inside a young cloud of glowing hydrogen, a blue-white star is burning so fiercely that its own light has begun to lift its outer skin into space. It is not dying yet. Its core is still alive, still turning hydrogen into helium, still pouring heat into the dark around it. But the light is no longer only light. It has become a pressure, a slow outward hand, pushing at the star from within. Before going further into that quiet and violent place, take a moment to settle in. If this kind of calm, deep space story belongs in the corner of your night, a like, a subscribe, or a share helps more than it may seem, and it lets the channel keep moving through these distant parts of the universe. If you are listening late or very early, write where you are watching from and what time it is there. It is always strange and comforting to imagine the same stars being heard from different rooms, different cities, different sides of the planet. Turn the lights down if they are still bright. Let the room become softer. Let a fan, an open window, or the low sound of the night take its place in the background. Find a position that asks nothing from the body. The story will move slowly enough. Out beyond the familiar yellow calm of the sun, there are stars that do not receive the gift of long life. They are born with too much weight, and that weight lights a fire they cannot keep for long. To understand why the brightest stars fade so quickly, it helps to begin with the one property that decides almost everything before the star has truly begun to shine. A star begins before it has a name, before any telescope could ever separate it from the darkness around it. It begins as a slow gathering inside a cold molecular cloud, where hydrogen, helium, dust, and faint traces of older stars drift for longer than any living memory could hold. Nothing in that cloud looks urgent at first. The gas is thin. The dust is quiet. The temperature is low enough that motion itself seems softened. Yet gravity is already at work, drawing one particle toward another, then another, until a darker knot forms inside the cloud and begins to fall inward under its own weight. That first weight matters more than almost anything that follows. Before the star has a color, before it has a surface, before it has a place on any diagram or a fate written into any model, it has mass. Mass decides how tightly gravity can squeeze the forming core. It decides how hot that core can become. It decides how quickly fusion will begin, how much light will be released, how strongly the outer layers will be held, and how long the star will remain itself. A star does not choose its life slowly as it ages. Much of that life is shaped during the collapse, when the cloud gathers enough material to ignite. The sun offers the gentlest place to begin. It is not small in human terms. It contains nearly all the mass of the solar system, holding planets, moons, comets, dust, and distant icy bodies in its wide gravitational reach. But among stars, the sun is moderate. It is a middle kind of star, neither faint and red nor blue and short-lived, with a surface that glows at about 5,500 degrees Celsius. Its light feels steady because, on the scale of life on Earth, it is steady. Inside its core, hydrogen nuclei fuse into helium, and the energy released through that fusion spends a long time working its way outward before it escapes as sunlight. This is what stability looks like. The sun is massive enough to burn, but not so massive that it consumes itself in haste. Its gravity presses inward, its heat and radiation press outward. Between those two forces, the star holds a quiet balance. It does not change quickly. It has already shone for about 4.5 billion years, and it will continue in its present state for billions more. From the ground on Earth, sunlight may seem immediate, but the star producing it is patient. Smaller stars are more patient still. Red dwarfs, the cool faint stars that fill most of the galaxy, burn slowly and may live for trillions of years. They give away their energy as if they were unwilling to spend it. At the other end of the stellar scale, the behavior changes completely. Add more mass to a forming star, and gravity presses harder on the core. The core heats. Fusion accelerates. More energy is released. And that energy pushes outward through the star in the form of heat and light. The first expectation might be simple. A star with twice the mass should shine twice as brightly, and a star with 10 times the mass should shine 10 times as brightly. Nature does not follow that gentle arithmetic. Luminosity rises much faster than mass. A star only several times heavier than the sun may shine hundreds of times brighter. A star 10 times more massive may shine thousands of times brighter. A star 50 or 100 times the mass of the sun may pour out light at a rate that belongs to an entirely different class of existence. The curve is steep. Every added layer of mass squeezes the core more strongly, and the fusion rate answers with a larger rise than intuition expects. In massive stars, the core is not simply warmer, it is driven into a different rhythm. This is why massive stars do not simply live as larger suns. Their interiors are not scaled-up copies of the solar core. They are hotter, denser, and more impatient. Their fuel supply is greater, but their hunger is greater still. A massive star may be born with many times more hydrogen than the sun. Yet, it spends that hydrogen so quickly that its life becomes far shorter. The rule feels backward at first. More fuel does not mean more time. For a star, more mass usually means more pressure, more heat, more light, and less time. This trade is one of the quiet keys to stellar evolution. The sun may live for around 10 billion years. A star 10 times its mass may survive for only tens of millions of years. A star far above that may last only a few million years before its core has moved beyond the long hydrogen-burning stage. On the scale of a galaxy, such a life is brief. A massive star can be born, shine, reshape the cloud around it, and die, while smaller stars formed nearby are still in the earliest calm stretch of their own lives. The color of a star is one of the ways this hidden pace becomes visible. Cooler stars look red or orange. Stars like the sun appear yellow-white from space, though Earth's atmosphere softens and colors that light. Hotter stars shift toward white and then blue-white. The blue color is not decoration. It is a signal that the surface is being heated by a powerful flow of energy from within. A blue star is telling the surrounding darkness that its core is working fast. Yet temperature alone is not enough. Two stars can have similar surface temperatures and very different total brightness if one is much larger than the other. A small hot star and an enormous hot star may both look blue in color, but the larger one has more surface from which to radiate. It sends more total light into space. This is why astronomers also speak of luminosity class, a way of separating ordinary main-sequence stars from giants, supergiants, and hypergiants. The classification marks how much space the star occupies, how much energy it releases, and how far it has moved from ordinary stability. The Sun belongs to the main sequence, the long band of stars that are still fusing hydrogen in their cores in a relatively steady way. Most stars spend the greater part of their lives there. Above that band are the giants and supergiants, stars that have grown larger and more luminous as their interiors change. Higher still, in the thin upper regions of the diagram, are the hypergiants. They are not common. The universe does not make many of them, and the ones it does make do not remain there for long. The path toward a blue hypergiant begins with the same simple condition as every other star. A cloud gathers enough mass. But in this case, the gathering is excessive. The forming star becomes so heavy that gravity drives the core into an intense state of fusion almost from the beginning. The light rising from that core is enormous. The surface becomes hot enough to shine blue-white. The star grows large enough that the area radiating this light is vast. Heat and size work together, and the luminosity climbs until the star is no longer merely bright in the ordinary sense. At that level, light begins to change its role. In the Sun, light is the outward sign of a stable engine. In a blue hypergiant, light is also part of the stress on the star. It is produced in such volume that it begins to push on the star's own matter with a force that can no longer be ignored. The same mass that made the star bright has created the conditions that will later make it unstable. The beginning already contains the ending. This is the first lesson hidden inside these blue stars. Their short lives are not accidents. They are not interrupted versions of calmer, stellar lives. They are the expected result of being born with too much mass for quiet endurance. The extra weight lights a stronger fire, and the stronger fire spends the star more quickly. Before any eruption, before any shell of gas has been thrown into space, before the star approaches the final edge of its life, the bargain has already been made. More power, less time. The next step is to look at what that power does when it grows beyond the range of ordinary giant stars. When blue light and immense size combine into a state so bright that gravity must struggle to keep the star whole. The first sign of a star's inner life is often its color. Long before the details of its core can be measured, before its mass is known precisely, before its future can be traced through models, the light itself carries a quiet message. A red star is spending its energy slowly. A yellow-white star, like the Sun, is burning at a middle pace. A blue star is different. Its surface is hot enough that the light shifts toward the shorter, sharper end of the visible spectrum, and that blue glow reveals a core where fusion is running at a much faster rate. Color, in a star, is not a mood. It is temperature made visible. A piece of metal in a forge first glows dull red, then orange, then yellow, and then white as more heat is driven into it. A star follows the same physical rule, though on a scale no forge could approach. Cooler stars radiate more of their light in redder wavelengths. Hotter stars pour out more blue and ultraviolet light. By the time a star is called blue, its surface temperature is far above the Sun's, and its radiation is strong enough to change the gas around it. Astronomers place these colors into spectral types, a sequence that runs from the hottest O-type stars through B, A, F, G, K, and M-type stars at the cooler end. The Sun sits among the G-type stars, steady and middle-toned. The red dwarfs that fill so much of the galaxy sit among the M-type stars, faint and long-lived. The blue stars belong mainly to the O and B types. They are bright, hot, and rare. The galaxy contains many more small, cool stars than massive hot ones, because small stars are easier to form and because they remain visible for far longer. This is one reason the night sky can be misleading. A blue star may appear as a clean point of light among many others, but it is not ordinary. It has already entered a faster kind of time. It is burning its fuel at a rate that makes its life brief, and the fact that it can be seen across such distances is not a sign of patience, but of expenditure. The star is visible because it is spending itself. A blue giant is the first step into that world. It is hotter and brighter than the Sun, often several times more massive, and its surface glows with the blue-white light of high temperature. If such a star replaced the Sun, the inner solar system would be overwhelmed by the increase in radiation. Worlds that now receive gentle sunlight would receive a flood of heat and ultraviolet energy. The habitable calm that surrounds a middle star would disappear. Yet a blue giant can still be understood as a star operating within a strong but manageable balance. Its gravity is powerful. Its core is hot. Its luminosity is high. Still, the structure can remain ordered for a time. The star is not gentle, but it is not yet at the far edge of what stellar physics allows. Its outer layers are still held with enough firmness that light does not completely take command of them. Beyond that lies the blue supergiant. Here the star is larger, brighter, and closer to the end of its main stability. a blue supergiant can shine tens of thousands or hundreds of thousands of times brighter than the sun. Its surface may not be the hottest possible surface in the universe, but it is spread across such a large area that the total light released is enormous. The star becomes visible over great distances, not only because it is hot, but because it is vast. Rigel, in Orion, gives a useful point of comparison. Seen from Earth, it is a blue-white light near 1 foot of the hunter, sharp and cold to the eye on clear winter nights. In physical terms, it is a blue supergiant, far more massive than the Sun and far more luminous. Its distance softens it into a star among stars, but that distance hides its scale. If a star like Rigel were placed near the Sun's nearest stellar neighbour, the night on Earth would no longer belong only to the Moon. Still, even Rigel does not fully describe the blue Hypergiant state. A blue supergiant is already immense, already short-lived, already moving through stellar evolution at a pace the Sun will never know. But a blue Hypergiant crosses another threshold. It is not only hotter or larger, it is luminous enough that the light moving through the star begins to act as one of the main forces shaping the star's body. The classification is not just a label of size, it marks a change in behavior. The difference becomes clearer on the Hertzsprung Russell diagram, the map astronomers use to place stars by temperature and luminosity. The main sequence forms a long path across that map, where stars spend the longest stable stretch of their lives. Giants and supergiants sit above it, brighter than ordinary stars of the same temperature because their surfaces have expanded and their total output has grown. At the top, in a thin region occupied by only a small number of known objects, the Hypergiants appear. They sit where the map begins to feel less like a catalogue and more like a warning. A blue Hypergiant occupies that upper blue region only briefly. It may carry dozens of times the mass of the Sun, sometimes more. It may shine more than 1,000,000 times as brightly. Its surface may be tens of thousands of degrees Celsius, and its outer layers may stretch far beyond the compact body imagined when the word star is heard. Heat and size combine there. The result is a star whose radiation fills the surrounding space with ultraviolet light, carving into nearby gas and making whole regions glow. These stars are usually found close to their birthplaces. They do not live long enough to drift far. A low-mass star can wander through the galaxy for billions of years, slowly changing its position while remaining almost the same kind of star. A blue hypergiant has no such time. It forms in a young and heavy cluster, where a molecular cloud has recently collapsed into many new suns, and it remains near the gas that gave it life. Around it, hydrogen can glow in broad red and pink clouds, while winds from the star cut cavities and arcs into the nebula. The star becomes a lamp inside the cloud that made it. There is a softness to these images when seen from a distance. A blue point, a red cloud, a cluster of young stars scattered like salt in darkness. The physics behind them is not soft. The ultraviolet radiation from the blue hypergiant strips electrons from nearby atoms. The stellar wind pushes gas outward. Dust grains warm and shine faintly in infrared light. Pillars and shells form where the outflow meets denser material. The entire region is being sculpted by one star whose lifetime will be shorter than the time many planets need to cool. This is the strange exchange blue light represents. The bluer and brighter a massive star becomes, the more quickly it moves through its store of fuel. The star's color is therefore also a sign of time running fast. A red dwarf can burn for ages longer than the current age of the universe. The sun moves through a measured middle life. A blue hypergiant, for all its size, is almost temporary. It shines like a signal that cannot last. That shortness does not make it less important. Because these stars live near young gas clouds, Their radiation and winds help decide what happens to the surrounding material. In some places, their light disperses gas and stops new stars from forming. In others, the pressure of expanding shells compresses nearby clouds, helping the next generation begin. The blue Hypergiant is not only a star inside a nebula, it is one of the forces that changes the nebula's future. From a distance, the star may look still. The eye sees a fixed point, the mind imagines permanence. But inside that point, fusion is racing, light is building. The outer layers are already feeling the first quiet pressure of the energy beneath them. The same blue glow that marks the star as hot and young also marks it as unstable in the making. It is beautiful because it is spending itself quickly, and its brightness is the visible surface of a much deeper imbalance. The next step is to follow that light inward and outward at the same time, from the core where it is born to the outer layers where it begins to push. Only there does the true nature of a blue Hypergiant become clear. Not simply as a bright star, but as a star whose own radiation is strong enough to loosen its hold on itself. The word hypergiant sounds, at first, like a simple increase in scale. A giant is large, a supergiant is larger, a hypergiant must be larger still. That is partly true, but it is not the part that matters most. In the upper reaches of stellar life, size alone no longer tells the story. A blue Hypergiant is not merely a blue supergiant with more radius and more light. It is a star that has crossed into a condition where the ordinary balance inside a star begins to lose its calm shape. A blue supergiant can be enormous and still hold together in a recognizable way. Gravity pulls its mass inward. Heat and radiation press outward. The balance may be intense, but it remains a balance. The outer layers can be disturbed by winds and pulsations, yet the star can still exist for a time as a coherent structure. It is powerful, but it is not always in open conflict with itself. A blue Hypergiant sits beyond that line. Its luminosity is so high that radiation is no longer simply energy escaping from the surface. It becomes a force with structural importance. Light, produced in the hot, dense core and carried outward through the star, begins to push on matter with enough strength to loosen the outer layers. The star is still held by gravity, but that hold has become less secure. The body of the star is no longer quiet beneath its own brightness. This is the shift that separates the hypergiant state from the supergiant state. The change is not only quantitative, it is behavioral. Below the threshold, a massive blue star can be hot, luminous, and short-lived, while still keeping its outer layers mostly attached. Above the threshold, the star begins to lose mass at a rate that changes its future. Wind is no longer a minor surface effect. Eruption is no longer an oddity. The star's own light has become part of the process that takes the star apart. The line is not sharp in the way a drawn border is sharp. Stars do not step across it in one clean moment. Their masses are uncertain, their distances can be difficult to measure, and their surfaces are not solid boundaries. Yet the pattern is clear. The most luminous blue stars behave differently. They show strong winds, unstable envelopes, irregular variability, and signs of material already thrown into the space around them. They carry evidence of a struggle that less extreme stars do not show in the same way. To imagine one of these objects, it helps to leave the quiet neighborhood of the sun. The sun drifts in a mature region of the galaxy, far from the dense cloud that formed it. A blue Hypergiant is usually much closer to its birthplace. It forms where star formation has happened recently, inside or near a young massive cluster. These are crowded places by stellar standards, built from cold molecular gas that has collapsed into many new stars at once. Most of those stars are smaller and calmer. A few are born with enough mass to change the region around them almost immediately. In such a cluster, a blue hypergiant, would not need to wait millions of years to make its presence known. Its ultraviolet radiation would pour into the surrounding gas, stripping electrons from hydrogen atoms and making the cloud glow. Around the star, an H2 region could open like a luminous cavity in the nebula. The gas would shine in reds and pinks, not because it is painted that way, but because ionized hydrogen is recombining and releasing light. The color would be the cloud's answer to the star. At the same time, the star's wind would move through the region. It would not be a breeze in the familiar sense. It would be a stream of charged particles and gas accelerated outward at enormous speeds, carrying mass away from the star and pushing into the surrounding medium. Where that wind meets denser gas, it can create arcs, rims, and shells. Where the radiation strikes dusty pillars, it can slowly erode them, leaving shapes that point back toward the blue source of their destruction. From far away, the region may look still. In reality, it is being carved. The blue hypergiant is therefore not only an object inside a star-forming region, it becomes one of the engines of that region. Its radiation heats and disperses gas. Its wind opens cavities. Its pressure can interrupt the birth of some stars while compressing nearby material enough to help other stars begin. The star has a short life, but its influence spreads outward through the cloud that made it. It changes the conditions of the place it will soon leave behind. This outward influence is one clue to its inner state. A star that can reshape a nebula over light years is releasing energy on a scale far beyond ordinary stellar life. Yet the same energy that sculpts the cloud also presses against the star itself. The nebula receives what the star cannot keep contained. Every glowing shell and curved filament around such a star is, in a quiet way, evidence that matter has been moved by light. The surface of a blue hypergiant is not a clean edge. It is a deep and restless atmosphere, extended outward by heat, radiation, and low effective gravity. The star's visible surface is the layer where light finally escapes freely. But above and below that layer, gas is moving, expanding, cooling, heating, and being accelerated into space. The boundary between star and wind can feel less like a wall and more like a shoreline in slow motion, with material constantly being lifted away. This is why blue hypergiants often look surrounded by their own history. The space near them may contain shells from older episodes of mass loss, rings of gas shaped by rotation or magnetic structure, and dust formed in cooled ejecta. These features are not decorations. They are records. A shell around a hypergiant marks a time when the star lost matter more strongly than usual. A ring may preserve the geometry of an eruption. A dusty envelope may hide the star from ordinary visible light while glowing softly in infrared wavelengths. The star is writing its past into the medium around it. It does this without intention, through pressure, radiation, and gravity, but the result is almost readable. The outer nebula shows that the star has already changed. The wind shows that it is still changing. The blue-white point at the center shows that the engine has not yet stopped. A blue hypergiant also changes on timescales that feel unusually close to human history. Smaller stars evolve so slowly that their lives appear frozen across generations. Even many massive stars seem steady over the span of a single observation program. But the most unstable luminous stars can brighten, fade, cool, swell, or shed material over years or decades. Their surfaces are not fixed, their winds vary. Their spectra shift as the layers above the core rearrange themselves. This does not mean the star is random, it means the physics is sensitive. When a star lives near the upper boundary of luminosity, small changes can have large effects. A slight change in the envelope can alter how radiation moves through it. A change in opacity can hold back energy for a time, raising local pressure. A small expansion can reduce the grip of gravity on the outer gas. The star responds through motion, through wind, through changes in brightness. The surface becomes a place where deep interior power shows itself indirectly. The blue hypergiant state is brief because it is unstable, but it is also brief because the star is evolving quickly beneath the surface. The core burns through fuel at a rapid pace. The envelope loses mass. The surrounding cloud is being pushed away. All of these processes happen together. The star is not waiting calmly for one stage to finish before another begins. It is changing in several ways at once. That is the meaning of the threshold beyond the supergiant line. It is the point where the star's light, mass, size, and age no longer behave as separate properties. They lock together. Mass creates the hot core. The hot core creates the luminosity. The luminosity pushes the envelope. The envelope escapes into the wind. The wind changes the mass. The changed mass alters the future of the core and the surface together. From far away, the blue hypergiant may still seem simple. A brilliant blue point set inside a glowing nebula. But inside that point is a system near the edge of stellar balance. Gravity is still present, still immense, still holding the star together for now. Light is rising from within, pressing outward with increasing authority. The star shines into space, and with every moment of that shining, it also pushes against the conditions that allow it to remain whole. The next layer of the story belongs to that pressure. The same light that makes the star visible across the galaxy is also carrying momentum, passing from photon to particle, from radiation to gas, until brightness itself becomes a physical hand on the star's outer layers. Light seems weightless because, in ordinary life, it almost always arrives too gently to be felt. Sunlight can warm a face, brighten a room, fade the color of cloth, and stir the chemistry of leaves, but it does not feel like a hand pressing against the skin. It passes through daily experience as illumination rather than force. The idea that light can push matter sounds strange only because the push is usually so small, yet light does carry momentum. Every photon, every small packet of electromagnetic radiation, can transfer a little motion when it is absorbed, scattered, or re-emitted. A single photon gives almost nothing. A stream of photons, arriving steadily for long enough, can become a measurable pressure. In the space around the sun, this pressure helps push tiny dust grains outward. It helps shape comet tails, pressing loose particles away from the sun while gravity pulls them inward. Even there, in the familiar solar system, light is doing quiet mechanical work. Inside a star, the same principle becomes much stronger. The radiation field is not a pale beam crossing a room. It is an enormous sea of photons born in a hot, dense core, moving outward through layers of plasma. Each photon travels, strikes an electron or ion, changes direction, gives up a little momentum, is absorbed, is re-emitted, and continues its slow outward journey. Deep in the star, this process repeats so many times that light may take a very long time to reach the surface. The path is not straight. It is a long wandering through matter. In the sun, radiation pressure is present, but it is not the dominant force. The sun's stability comes from a balance between inward gravity and outward pressure, mostly from hot gas and radiation together. The core is hot because gravity has compressed it. The heat and energy produced by fusion resist further collapse. When the balance is right, the star holds its shape. This state is called hydrostatic equilibrium, a quiet phrase for one of the most important balances in the universe. For the sun, the balance is comfortable. If the outer layers shift slightly, the star has ways to settle back. A small contraction raises temperature and pressure, pushing the material outward again. A small expansion cools the gas and lets gravity draw it inward. The system corrects itself over and over, not perfectly, but reliably enough that the sun changes only very slowly. It is not close to the edge where light could lift its outer layers away. Massive stars live under a different balance. Their gravity is stronger because more mass has been gathered into the star. But their luminosity rises even faster. The extra mass compresses the core, the hotter core drives fusion more rapidly, and the radiation moving outward grows enormously. Gravity has increased, but light has increased more. With each step toward higher mass, the star moves closer to the place where radiation pressure can no longer be treated as a secondary detail. This is where the Eddington limit enters the story. The limit describes the luminosity at which the outward force of radiation on the outer layers of a star balances the inward pull of gravity. Below that limit, gravity can hold the star together. At the limit, the two forces are matched in a delicate way. Above it, at least in the simplest picture, light pushes hard enough to drive material outward. The star can no longer keep all of its outer gas bound. The Eddington limit is not a wall made of stone. It is a boundary in behavior. A star can approach it gradually, and different layers inside the star may feel the balance differently. Some parts of the envelope may remain bound while other regions become loose and vulnerable. Local changes in temperature, density, and opacity can make one layer experience a stronger radiative push than another. The star does not have to exceed the limit everywhere to become unstable. It only needs regions where light finds enough material to push. A sun-like star is far from this state. Its light is steady, but its gravity has a wide margin of control. A blue hypergiant has no such margin. Its luminosity can reach a large fraction of its Eddington luminosity, leaving the outer layers only weakly held. The star still exists because gravity has not lost completely, but the balance has become thin. The surface is no longer a firmly attached skin. It is more like an atmosphere lifted and loosened by the intensity rising beneath it. The pressure of light acts most strongly where photons interact often with matter. Pure hydrogen and helium can be pushed, but metals are especially important in stellar envelopes. In astronomy, metals means elements heavier than helium. Iron, with its many electron transitions, can absorb and scatter radiation through many different channels. When photons meet ions like these, momentum passes from light into gas more efficiently. The star's brightness becomes a wind-making force. This is how radiation-driven stellar winds begin. The photons escaping from the star push on ions in the outer layers. Those ions move outward and drag surrounding gas with them through collisions and electromagnetic coupling. What begins as a transfer of momentum from light to individual particles becomes a large flow of matter leaving the star. In a modest star, the flow is thin. In a blue hypergiant, it can become one of the strongest winds produced by any normal star. The wind does not look like a simple stream pouring evenly from a smooth surface. The star's atmosphere is turbulent, extended, and sensitive. Some regions may become denser than others. Some may absorb radiation more effectively. Some may be lifted, cooled, and pushed farther out before settling into the general outflow. The result is a wind that can carry clumps, shells, and uneven structures into the space around the star. Over time, these structures build the first layers of the circumstellar environment. The important point is that the star is losing itself while it shines. The light is not merely escaping, it is carrying matter away. Every year, a small part of the star that once belonged to the envelope is added to the surrounding space. In ordinary language, it may sound like a loss too slight to matter. For a blue hypergiant, over thousands of years, the effect becomes decisive. A wind strong enough to remove even a tiny fraction of a solar mass each year can eventually strip away many suns' worth of material. As mass leaves, the balance changes again. Gravity depends on the amount of mass left behind. The luminosity, however, can remain enormous because the core is still burning at a furious rate. The star becomes lighter while still shining with nearly the same force. This pushes the outer layers closer to instability. Mass loss can therefore encourage further mass loss. The star moves into a loop where each layer removed makes the next layer easier to lift. That loop is one reason blue hypergiants cannot rest. A stable star dampens disturbances. A blue hypergiant can amplify them. A slight swelling of the envelope may lower the effective gravity in the outer gas. Lower effective gravity allows radiation to lift the gas more easily. The lifted gas expands, cools, and may change its opacity, allowing certain layers to trap or absorb more radiation. The pressure rises in places where the structure is already weak. A small change grows. This does not mean the star is exploding in every moment. Most of the time, it remains a star, with a core, an envelope, a wind, and a luminous surface. But the surface is alive with instability. It can pulsate. It can brighten or dim. It can shed more material during one period and less during another. In some phases, the mass loss may become so strong that the wind thickens into something closer to an outburst. The star does not need an outside disturbance. Its own light is enough. The outer atmosphere is the place where this conflict becomes visible. Deep below, density is high, and gravity still has a strong grip. Photons are trapped in a dense interior, scattered again and again as they work outward. Near the surface, the density falls. Photons move more freely. Gas is less tightly bound. The same radiation that was part of an interior balance now becomes a surface escape mechanism. The star's edge is where the pressure of light finds its easiest path into space. Around the star, the result is a faint expanding record. Gas moves outward. Dust may later condense in cooler parts of the ejecta. Ultraviolet radiation lights nearby hydrogen. Older shells drift farther away, while newer winds catch up from behind. The environment begins to resemble a series of slow waves spreading through darkness, each one made of matter that once helped form the star's body. The Eddington limit, then, is not just a number attached to a model. It is a way of describing how close a star is to losing the ordinary authority of gravity over its light. A blue hypergiant lives close enough to that boundary that brightness becomes dangerous to structure. The star's beauty, seen from far away as a blue-white point in a glowing cloud, is produced by the same energy that makes its surface vulnerable. In the next layer of the story, this vulnerability becomes more specific. The star's outer fire is not smooth. Certain elements, especially iron, can hold back radiation in hidden layers below the visible surface. There, light gathers pressure inside the envelope, and the quiet push of photons can become the beginning of deeper instability. Near the Eddington edge, a star no longer behaves like a sealed sphere. It is still held together by gravity, still burning in its core, still recognizable as a star, but the outer layers have become less certain of their place. The surface is not a firm boundary. It is a deep, bright, moving atmosphere where gas can be lifted, stretched, cooled, heated again, and carried outward by light. In a calmer star, gravity gives the outer layers a clear downward direction. Material may rise through convection or move in waves, but it remains strongly tied to the body beneath it. If gas is displaced upward, gravity pulls it back, unless some other force continues to support it. The star breathes in small ways and then settles. Its disturbances are folded back into balance. A blue hypergiant has a much weaker margin. Its gravity is still immense, but its luminosity is immense as well, and the radiative push through the envelope reduces the effective weight of the gas. The material near the surface feels less bound than it would in a dimmer star of the same mass. It can be nudged outward more easily. A layer that begins to rise may not fall back quickly. It may expand, thin, and drift into a region where photons can push it with still greater efficiency. This is the meaning of living close to the Eddington limit. The star is not necessarily beyond control everywhere, but the control has become fragile. Gravity and radiation are close enough in strength that the ordinary restoring forces of a star lose some of their firmness. The envelope becomes inflated, its density drops, its outer regions grow extended and vulnerable, like a mist held near a flame. The visible surface of such a star may sit far above the deeper layers where most of the mass still resides. Between the core and that surface lies an envelope full of gradients. Temperature falling outward, density thinning, radiation pushing through, ions absorbing and scattering light, gas trying to settle while energy tries to escape. The star is layered, but the layers do not behave like quiet shells. They respond to one another. A change in one region can move outward and alter the next. A small increase in the energy flowing through the envelope can raise the local radiation pressure. That pressure lifts gas. Lifted gas expands. Expanded gas can become less dense and less tightly held by gravity. In some temperature ranges, the opacity of the gas can increase, making it absorb more radiation rather than less. The extra absorption raises the pressure again. A small movement becomes a larger one. This is not the smooth self-correction seen in a more stable star. It is closer to a slow amplification. The star does not need to be struck from outside. It carries the source of disturbance within its own structure. The core continues to supply energy. The envelope tries to pass that energy outward. The outer layers, already near the edge of escape, answer with motion. The most constant expression of this motion is the stellar wind. Every hot, luminous star has some kind of wind, but in a blue hypergiant, the wind can become a major part of the star's evolution. It is not just a faint loss from the surface. It is a river of ionized gas leaving the star at high speed, driven by radiation that transfers momentum to atoms and ions in the upper atmosphere. The star shines, and because it shines so strongly, it also sheds. The flow begins in layers too thin to look like the body of a star and too dense to be empty space. Photons moving outward strike ions, especially metal ions, and give them tiny outward pushes. Each push is small. The number of pushes is not. The ions accelerate and drag surrounding particles with them. The gas becomes part of the wind. It crosses the point where gravity can no longer reclaim it and moves into the circumstellar space around the star. Over a single year, the amount lost might seem small beside the mass of the whole star. Over many thousands of years, it becomes the story of the star's changing body. A blue hypergiant may lose entire solar masses through wind and outburst before it reaches the end of its life. Matter that once pressed down on the core is gone. Matter that once helped define the star's envelope becomes part of a shell, a stream, a distant glow. The wind also changes what the star looks like. Its spectrum carries signs of outflow. Certain emission and absorption features show that gas is moving away from the star, sometimes in a dense and fast wind. The light arriving at a telescope is no longer only the light of the surface. It has passed through moving material, through an atmosphere that is escaping. In those spectral lines, astronomers read the motion of gas the eye could never separate on its own. The strongest winds are not perfectly even. A star near the Eddington edge may shed more from one region than another. Rotation can make the equator and poles behave differently. Pulsations can thicken some layers and thin others. Magnetic fields, when present, may guide charged particles in subtle ways. The wind becomes textured. It carries clumps and waves, denser knots and clearer gaps, all moving outward through the star's own light. Beyond the steady wind are the greater episodes. the outbursts that make the blue Hypergiant and its close relatives so difficult to treat as ordinary stars. During such a phase, the outer envelope can expand dramatically. The apparent surface can cool, even as the total luminosity remains very high. More of the star's radiation shifts into visible wavelengths, so the star can appear brighter to human eyes without needing its total energy output to rise by the same amount. The body of the star changes its expression. In stronger events, the process becomes more than expansion. Material is expelled. A shell forms. The star throws off part of its outer envelope and leaves that material traveling outward, where it may glow in the star's light, or later cool enough for dust to form. The core survives. The star remains alive. But it is altered. The gas around it now holds the shape of a past instability. These eruptions do not need to be final explosions. That distinction matters. A supernova destroys or transforms the core. An eruption from a luminous blue variable or blue hypergiant can be enormous and still leave the star standing. The energy is released through the envelope, through radiation pressure, expansion, and ejection, while the nuclear engine continues beneath. From far away, the event may resemble a death. In reality, it is a violent change of state that the star survives, at least for a while. Eta Carinae is the clearest nearby memory of such behavior. In the 19th century, it brightened until it became one of the brightest stars in the sky. Though it lies thousands of light years away, it did not vanish in a supernova. Instead, it expelled a vast amount of material and formed the homunculus nebula, a bipolar cloud expanding away from the central system. The nebula is not an afterimage. It is the star's own discarded matter, still moving outward, still carrying the record of that eruption. P Cygni offers another kind of record. It brightened suddenly in the early 17th century and then faded, leaving behind evidence of a powerful outflow. Its spectrum became important enough that a whole type of spectral feature carries its name, a pattern that reveals gas expanding away from a star. A P Cygni profile is light shaped by motion, emission from the wind and absorption from material moving toward the observer while leaving the star behind. It is one of the quiet signatures of escape. Near the Eddington edge, such signatures are expected. They are the marks of a star whose atmosphere has become too lightly held for complete stillness. The envelope is not simply warmed from below, it is lifted. It is exposed to a radiation field strong enough to turn brightness into motion. It is altered by every layer it loses because removing mass changes the balance that allowed the star to remain in that state. This creates a slow narrowing of possibility. As the star loses mass, its gravitational hold weakens. The luminosity generated by the core does not fall at the same pace. The ratio between outward radiative force and inward gravity shifts toward the outward side. The star approaches the edge again, sometimes more closely than before. Wind prepares the way for outburst. Outburst removes mass that makes later wind more effective. The process feeds on its own consequences. The result is not a stable identity, but a passage. A blue hypergiant is not a place where a star settles for long. It is a condition crossed while the star is losing the ability to remain what it is. The outer layers drift away. The wind thickens and thins. Shells form around the star, like faint pages of a history written in gas. The light that made the star visible across the galaxy is also the light that is loosening its surface, year by year, layer by layer. At the deepest level, the core still burns, hidden below all this motion. It does not see the surface directly. It continues to produce energy according to the pressure and temperature inside it. Above it, the envelope carries that energy outward and pays the price. The closer the star lives to the Eddington edge, the more every photon matters. Because every photon leaving the star may also help carry a little of the star away, there is another hidden layer to this instability. Light does not pass through all material equally. In certain regions below the surface, iron and other heavy ions can trap radiation more effectively, building pressure in places where the star is already delicate. The edge is not only at the surface, it is buried inside the outer fire, where opacity can turn a flow of light into a swelling force. Below the visible surface of a blue hypergiant, far beneath the blue-white light that escapes into space, the star contains layers that cannot be seen directly, but still shape everything that happens above them. The surface is only the last place where light becomes free. Before that freedom, radiation must pass through gas that changes with depth, pressure, temperature, and chemical composition. In some layers, light travels more easily. In others, it is held back. This holding back is called opacity. It is a measure of how strongly matter blocks, absorbs, or scatters radiation. A transparent window has low opacity to visible light. A curtain has higher opacity. Inside a star, the curtain is not cloth but plasma, a hot mixture of ions and free electrons. The radiation moving outward from the core meets this plasma again and again, and every interaction changes how energy flows through the envelope. Opacity matters because light is not only carrying energy, it is carrying pressure. When a layer of stellar material becomes more opaque, radiation has more difficulty passing through it. Energy can build up below or within that layer. The local pressure rises. The gas responds by expanding, moving, or becoming unstable. In a star already close to the Eddington limit, this change does not need to be large to matter. Iron plays a special role in this hidden part of the story. In ordinary speech, iron may feel heavy, dark, and solid, something found in tools, rails, or the cores of planets. Inside the outer envelope of a blue hypergiant, iron is not solid at all. It is stripped of many of its electrons by heat. It exists as ions in a sea of plasma, surrounded by radiation flowing outward from deeper regions. Even in that stripped state, iron retains a complicated atomic structure. It can interact with light through many possible transitions. That complexity makes iron unusually effective at absorbing and scattering radiation in certain temperature zones. At depths where the temperature reaches roughly the range in which ions have just the right electron structure, the opacity can rise sharply. This rise is known as the iron opacity bump. It is not a bump that could be seen as a shape inside the star. It is a region where the material suddenly becomes better at catching the outward moving light. The image is simple enough. Radiation is trying to pass outward like water, moving through a deep channel. Most layers allow some flow, though not freely. Then the radiation meets a region where ions catch it more effectively. The flow slows, energy gathers, pressure increases. The layer above feels that added pressure from below and can begin to lift. In a stable star, this might be absorbed into the ordinary balance of the interior. The star would adjust, and the disturbance would be limited. In a blue hypergiant, the outer envelope is already close to losing its grip. Gravity has been weakened in effect by the enormous luminosity pressing outward. The surface layers are extended and lightly bound. When radiation pressure builds under one of those layers, the response can be much larger. The iron opacity bump can help inflate the envelope. It can create zones where convection begins, because radiation alone has difficulty carrying energy through the opaque region. Gas starts to move in larger currents, carrying heat upward through motion rather than radiation alone. These motions can disturb the layers above them. They can feed pulsations, thicken parts of the wind, and make the star's surface less regular. The star becomes less like a smooth, glowing sphere and more like a deep fluid body struggling to pass too much light through too little stability. This is one of the hidden reasons the outer parts of blue hypergiants are so difficult to predict. The star's brightness may be known. Its temperature may be estimated. Its spectrum may reveal a strong wind, but beneath the surface, small changes in opacity can alter how energy moves. The envelope can respond in ways that are slow, uneven, and layered. A change that begins where iron catches radiation may appear later as a change in wind, radius, temperature, or brightness. The process is not always violent in appearance. Sometimes it may show as a subtle pulsation, a slow expansion and contraction of the outer layers. Sometimes it may thicken the stellar wind. Sometimes it may help prepare the conditions for a larger outburst. Not as the only cause, but as part of a chain of instability. In these stars, causes do not act alone. Radiation pressure, opacity, rotation, mass loss, and the changing core all influence one another. The iron opacity bump is especially important because it lies in a region where the star is neither deep enough to be fully secure nor shallow enough to be simple atmosphere. It is in the envelope, in the broad outer body of the star, where material still belongs to the star, but is already affected by the pressure trying to send it outward. That region is a threshold inside the threshold. It is not yet wind, but it can help make wind. It is not yet eruption, but it can help weaken the layers that eruption will later remove. A blue hypergiant therefore carries one of its instabilities in the chemistry of its own plasma. The same elements forged by earlier generations of stars, mixed into the gas cloud from which the blue hypergiant formed, now help control how the new star loses mass. Iron atoms born long before this star existed become part of the mechanism by which its light pushes outward. The history of the galaxy is folded into the envelope of the star. There is a quiet connection here between the very small and the enormous. An iron of iron is tiny beyond ordinary imagination, far smaller than any grain of dust. Yet the interactions of countless iron ions with countless photons can influence the behavior of a star whose light shapes a nebula across light years. The star's largest visible changes may depend in part on microscopic transitions inside its plasma. Scale does not separate these things. In stellar physics, the smallest structures can help decide the motion of the largest bodies. The opacity bump also helps explain why stars near this limit do not always behave in a steady way. If the radiation flow through one layer changes, the layer may expand. Expansion cools the gas. Cooling can change the ionization state of iron and other metals. A different ionization state changes opacity again. The flow of radiation changes in response. The layer moves once more. This feedback can make the envelope breathe unevenly, not with the calm rhythm of life, but with the physics of trapped light and shifting matter. A distant observer may see only the result. The star becomes slightly brighter or dimmer. Its spectral lines change shape. The wind grows denser. The apparent temperature drifts. A shell of material appears years or centuries later, expanding away from the star. Behind those observations lies a deeper structure where radiation found a place to gather, where iron helped hold it back, where pressure rose until the envelope answered. This does not mean every outburst can be reduced to iron alone. The lives of blue hypergiants are more complicated than that. Rotation can flatten a star and change how matter leaves it. A companion star can pull on the envelope or exchange mass. The core's evolution can shift the energy moving outward. The surface can be altered by previous eruptions and by the material already surrounding the star. But the iron opacity bump remains one of the important hidden mechanisms because it shows how instability can be built into the star's own layers. The word hidden is useful here. A blue hypergiant is bright enough to dominate a cluster, yet some of its most important behavior begins where sight cannot reach. The eye sees the blue surface, A telescope records the spectrum. Infrared instruments may detect warm dust around it. Models then look inward, following pressure, opacity, and radiation into the envelope. The star is red from the outside, but the causes are buried. In that buried region, light is delayed, not stopped forever, but slowed, scattered, redirected, and made more forceful by the very matter it is trying to pass through. The envelope becomes a place where escaping energy has consequences before it ever reaches space. Each photon that is absorbed or scattered helps transfer momentum. Each layer that grows more opaque receives more of that pressure. The star's own brightness works through its own chemistry. This changes the way the blue hypergiant should be imagined. It is not only a blue flame in space, not only a giant sphere losing gas from its surface. It is a layered object in which the outward journey of light is full of resistance. In the deepest core, fusion makes energy. In the envelope, iron and other ions decide how easily that energy can pass. Near the surface, the same energy becomes wind. Outside the star, that wind becomes nebula. One process becomes the next. The iron in the outer fire is therefore part of the bridge between the star's hidden interior and its visible surroundings. It helps explain how a star can be bright for a long time and then suddenly change its wind, its radius, or its apparent temperature. It helps explain why the surface seems restless even when the core has not collapsed. It gives the envelope a memory of pressure, a place where radiation can gather before motion follows. Far from the star, the surrounding gas may glow calmly in blue and red light. Shells may drift outward so slowly on the scale of the sky that they seem almost fixed. But each shell began as a decision made by physics inside the star. Pressure exceeding restraint, opacity shaping escape, radiation lifting matter past the point of return. The beauty outside is connected to the difficulty inside. This hidden opacity also opens the way to another part of the story. The strength of radiation-driven mass loss does not depend only on how much mass the star was born with. It also depends on what that mass is made of. The elements mixed into the star, especially the metals that catch light so effectively, can change how strongly the star's own radiation can peel it apart. A blue hypergiant's fate is written not only in its weight, but in its composition. A star is often described by its mass, its temperature, and its light, but those are not the only things written into its future. The material itself matters. The gas that collapses into a star is never just weight without memory. It carries hydrogen and helium, the old simple elements left from the early universe, and it also carries small traces of heavier elements made by stars that lived and died before it. Those traces may seem slight beside the huge reservoir of hydrogen, but in the life of a blue hypergiant, they can change the way light escapes and the way matter is lost. Astronomers call these heavier elements metals, even when the word does not match ordinary chemistry. Carbon, oxygen, neon, silicon, iron, and many others all count as metals in this language because they are heavier than helium. The amount of them in a star is called metallicity. A star with high metallicity contains more of these heavy elements mixed into its gas. A star with low metallicity contains fewer. That small difference can decide how easily radiation grips the star's outer layers. At first, this may seem like a detail. A blue hypergiant is mostly hydrogen and helium by mass. Its great luminosity comes from fusion in the core, not from the small fraction of metals in its envelope. Yet the photons moving outward do not care only about what is most abundant. They care about what they can interact with. Hydrogen and helium can scatter radiation, but many metal ions provide far more ways for photons to be absorbed and redirected. They give the light more handles. This is where composition becomes fate. A massive star rich in metals can drive a stronger wind, because its radiation has more opportunities to transfer momentum to the gas. Metal ions absorb photons, receive a push, and help drag the surrounding plasma outward. The wind grows thicker, mass leaves faster. The star is peeled more quickly by its own light. In a blue hypergiant already near the Eddington edge, that extra efficiency matters. A star with lower metallicity may shine with enormous power and still lose mass differently. Its radiation is intense, but there are fewer metal ions to catch that radiation and turn it into outward motion. The wind can be weaker. The star may hold onto more of its mass for longer. It may reach later stages of life with a heavier core than a similar star born in a metal-rich environment. The same initial mass does not always lead to the same ending. This is a quiet correction to the simplest version of the story. Mass is the first great decision in a star's life, but it is not the only one. A blue hypergiant born in one part of cosmic history may not behave exactly like a blue hypergiant born in another. The universe changes with time. Early generations of stars formed from gas that had not yet been enriched by many supernovae. Later stars formed from clouds seeded with carbon, oxygen, iron, and dust from older stellar deaths. Every generation inherited a different chemical background. In the earliest universe, before many stars had died, the gas was almost entirely hydrogen and helium. The first stars, sometimes called population 3 stars, are thought to have formed with extremely low metallicity, perhaps with no metals at all. No such star has been observed directly, because they would have lived and died long ago if the models are correct. But their possible existence matters for understanding the upper limits of stellar mass. With few metals to drive winds, the first very massive stars may have kept more of their birth mass until the end. That possibility changes the picture of stellar death. A metal-rich massive star can lose so much material that it ends as a stripped core, perhaps becoming a Wolf-Rayet star before collapse. A metal-poor massive star may retain a larger envelope or build a heavier core. If the core becomes heavy enough, different endings become possible. Pair instability, direct collapse, or the formation of a large black hole all depend partly on how much mass remains when nuclear burning reaches its final stages. The wind, shaped by metallicity, helps decide what is left. The same principle also reaches across galaxies. Not every galaxy has the same chemical history. Large spiral galaxies, dwarf galaxies, starburst regions, and the outskirts of galaxies can have different metallicities. A massive star born in a metal-poor dwarf galaxy may lose mass in a different way from one born in a metal-rich region of the Milky Way. This means the most extreme stellar deaths are not distributed evenly through the cosmos. They are tied to the chemical age and environment of the place where the star was born. This becomes especially important for black holes. Some of the heavy black holes detected through gravitational waves are thought to have formed from massive stars in low metallicity environments. The reason is simple in outline. If a massive star loses less mass through winds, it can leave behind a heavier core. A heavier core can collapse into a heavier black hole. The light that failed to strip the star completely during life may allow gravity to keep more material at the end. Blue hypergiants sit within this larger pattern. In a metal-rich environment, their winds can be dense and powerful, filling the space around them with expelled gas and dust. In a lower metallicity environment, similar stars may remain more compact or retain more mass, depending on rotation, mixing, and binary interaction. The category remains recognizable, but the path through it shifts. The blue hypergiant state is not a single road. It is a narrow weather system created by mass, light, chemistry, and time. Metallicity also affects what can be seen. A star losing mass through a metal-rich wind may create a dense circumstellar environment. Gas flows outward. Dust can form later in cooler regions. The star may become partly hidden by the matter it has expelled. Its visible light may be dimmed or reddened, while infrared radiation from warm dust grows stronger. The chemistry of the wind helps shape not only the star's evolution, but the way it appears to distant observers. A star with fewer metals may leave a cleaner space around itself, though not always. Rotation can mix material upward. A companion can strip or disturb the envelope. Late burning stages can alter surface abundances. No single factor rules alone. Still, metallicity remains one of the quiet levers behind the visible drama of massive stars. It changes how strongly light couples to matter. And in stars where light is already close to overpowering gravity, that coupling becomes a major part of the story. There is also a deeper link between metallicity and the stars that came before. The metals inside a blue hypergiant did not begin there. Carbon may have been made in an older red giant. Oxygen may have been forged in the core of a massive star. Iron may have been released by a supernova or built in a star that ended violently long before this one formed. When those elements enter a new molecular cloud, they become part of the next star's behavior. A past explosion can influence a future wind. The galaxy is therefore not only a collection of separate stars, it is a chain of inheritance. One generation makes heavy elements, another generation forms from them. Those elements alter opacity, cooling, wind strength, dust formation, and the final mass of later stars. The death of an old star can help decide how quickly a new blue hypergiant loses its surface. The physics is local, but the history is galactic. This gives the blue hypergiant a different kind of depth. It is not only extreme because it is massive, it is extreme because it stands at a crossing point between the early simplicity of hydrogen and helium and the later richness of heavy elements. Its light is born from fusion in the core, but its escape is shaped by metals in the envelope. Its wind is driven by photons, but those photons need ions to push against. Its fate is determined by gravity and nuclear burning, but also by the chemical memory carried into the star at birth. A blue hypergiant in a metal-rich cluster may spend its short life surrounded by a thickening record of its own loss. The wind lifts material from the surface. The gas expands into the surrounding nebula. Dust gathers in cooled pockets. Shells form where one episode of outflow meets another. The star becomes increasingly wrapped in evidence of the same process that is reducing it. Its brightness makes the wind makes the veil. A blue hypergiant in a lower metallicity place may follow a quieter outward loss, at least in its steady wind. It may keep more mass until later, when the core has advanced closer to collapse. Its final explosion, if one comes, may differ from the death of a similar star born in a richer cloud. In this way, the same kind of star can become several different endings, depending on the small heavy ingredients mixed into the gas before the star began. The secret is not that metals dominate the star by quantity. They do not. The secret is that they dominate certain interactions. A rare ingredient can matter if it is the one that catches the light. A trace element can guide the flow of radiation. A small fraction of the mass can alter how the whole envelope responds. In the outer layers of the most luminous stars, the minor components can have major consequences. This is why the story cannot stop at size. A blue hypergiant is born from weight, but it is sculpted by composition. Its mass lights the furnace. Its metals help decide how strongly that furnace peels the star apart. The surrounding galaxy provides the ingredients, and the star returns them changed. Mixed with new material from its interior, carried outward by winds, and later by whatever ending awaits. The next part of the journey follows what happens when a star, this luminous, tries to move across the map of stellar evolution. There are regions where such a star cannot remain. places where high luminosity and cooler temperatures become a dangerous combination. Near that boundary, the star may swell, brighten, shed matter, and be forced back by its own instability, leaving the shape of its struggle in the gas around it. The life of a massive star can be drawn as a path across a map. The map is not made of land or ocean, but of temperature and luminosity. On one side, stars are hotter. On another, they are cooler. Higher up, they shine with greater power. Lower down, they release their light more quietly. This map, the Hertzsprung Russell diagram, gathers stars into patterns that reveal where they are in their lives and how they are changing. For ordinary stars, the paths across this diagram can be slow and graceful. A sun-like star spends most of its life along the main sequence, burning hydrogen in its core with little outward change. Later, as the core changes, it moves into a giant phase, swelling and cooling while its outer layers expand. The movement is real, but it happens over spans of time too long for human eyes to follow directly. The star crosses the diagram like a shadow moving across a wall too slowly to notice. The most luminous, massive stars do not always receive that slow freedom. When a blue hypergiant tries to evolve away from its hot blue state, it approaches a region where the usual paths become difficult. Its interior is changing. Its core is moving through fuel. Its envelope wants to expand and cool. On the diagram, the star should drift toward lower surface temperatures while keeping much of its enormous luminosity. But at the highest luminosities, that crossing becomes unstable. This observed boundary is known as the Humphreys-Davidson limit. It was not first recognized as an abstract line drawn by theory alone. It emerged from the study of very luminous stars in the Milky Way and nearby galaxies. When astronomers placed these stars on the Hertzsprung Russell diagram, they noticed that certain regions were strangely empty. Above a high luminosity, stars did not appear to remain as cool, yellow, or warm supergiants in the way simpler expectations might allow. There was a missing territory. The absence is telling. Stars are not avoiding that region by chance. At very high luminosities, the outer layers of a massive star become too unstable when the star expands and cools. The balance between gravity and radiation pressure, already thin in the blue hypergiant state, weakens further. The envelope grows larger and less tightly bound. Opacity changes. Radiation becomes trapped in places. The star is pushed toward mass loss, just when it is trying to move into a cooler configuration. A less luminous star can become a red supergiant and remain there for a time. Its envelope expands, its surface cools, and its large radius allows it to shine brightly without living at the very edge of radiative instability. A star of far greater luminosity faces another situation. Expansion can lower the effective gravity in the outer layers. Cooling can shift the ionization of elements in ways that increase opacity. Radiation pressure can build beneath the surface. The star moves toward a state it cannot hold. The result is not a clean crossing. It is an interrupted one. The star may swell and cool, then shed mass and retreat. It may brighten in visible light as its radiation shifts from ultraviolet into wavelengths the eye could see. It may form a denser wind, or an expanding shell, or a deeper atmosphere that looks cooler from outside, while the total luminosity remains high. The star seems to be moving across the map, but the map itself resists. This is the world of luminous blue variables. These stars are among the closest relatives of blue hypergiants, and in many cases, they may represent a phase of the same kind of extreme evolution. A luminous blue variable is not quiet. It changes brightness, temperature, radius, and wind strength over years or decades. In some phases, it appears as a hot blue star. In others, it expands and cools. becoming visually brighter, while its deeper energy output remains in the same high range. The surface expression changes because the envelope changes. The name variable may sound modest, as if the star were only flickering. The reality is deeper. The star is attempting to adjust its structure while living too close to the upper edge of luminosity. Its outer layers are sensitive to pressure, opacity, and mass loss. The variations are not small decorations added to a stable star. They are signs that the star cannot settle comfortably into the next state. During a calmer phase, a luminous blue variable may hold a hot compact appearance. Its wind may remain strong, but steady enough to be described. Then the envelope expands. The apparent surface moves outward into cooler layers. The star's visual brightness rises, not always because its total energy output has grown greatly, but because more of its energy emerges in visible light instead of ultraviolet. To an observer, the star has brightened. To the star itself, the envelope has shifted. If the expansion continues into a region where the outer layers are weakly bound, radiation pressure can drive stronger mass loss. The wind thickens. Gas is lifted away. Sometimes the event remains a wind change or a moderate outburst. Sometimes it becomes a larger eruption, leaving a shell that drifts outward for centuries. The star then contracts or heats again, returning toward the blue side of the diagram. It has not crossed smoothly. It has been pushed back by its own instability. This cycle gives the Humphreys-Davidson limit its physical meaning. It is not simply an empty space on a chart. It is a sign of what happens when luminosity, temperature, opacity, and gravity reach an unsuitable combination. The star is too bright to become cool and extended without losing control of its outer layers. It tries to become something else, and the attempt itself removes mass. Eta Carinae gives this idea a visible form. Its great eruption in the 19th century did not destroy the star, but it expelled a large quantity of material into space. The homunculus nebula now surrounds the central system, shaped like two opposing lobes, expanding away from the star. This structure is a memory of an episode when the outer layers were driven outward with force enough to change the star's future. The star survived, but it did not remain the same. Eta Carinae carries another record of this unstable passage. It is surrounded by a shell of material lost in earlier phases of its life. Its brightness and temperature have varied over time, showing the pattern of a massive luminous star shifting between hotter and cooler states. Around it, the nebula is a quiet ledger of the matter that could not remain attached. Each particle once belonged to the star. Each now travels outward, lit by the same source that helped release it. S. Doradus, in the Large Magellanic Cloud, gave its name to a class of variability seen in luminous blue variables. Its changes are not random flashes, but part of a broader pattern among the most luminous, unstable stars. They move in brightness and temperature because their envelopes are close to a limit where small structural shifts can grow. The star's appearance becomes a slow weather of light. There is a gentle way to imagine the process. The blue Hypergiant begins high and hot on the stellar map, shining with blue-white radiation. Its core evolves. The envelope responds by expanding, trying to move the visible surface outward and cool. The star approaches the forbidden upper region. The outer layers loosen. Radiation pressure rises in its influence. Wind strengthens. A shell may be thrown away. The star loses mass and turns back toward a hotter state. Not because it has chosen to, but because the path forward could not be held. Every cycle reduces the star. The loss may be gradual through wind or sudden through eruption. Either way, the envelope becomes lighter. The gravitational hold changes. The chemical surface may change as deeper material is exposed. The surrounding nebula grows richer and more structured. The star leaves behind evidence of each failed crossing. The timescale is short by stellar standards. A luminous blue variable phase may last only tens of thousands of years, perhaps less for some stars. Against the life of the Sun, this is almost nothing. Against human history, it is long enough for eruptions to be recorded, for brightness changes to be noticed, for the star to become a known presence in the sky and then fade. These objects bring stellar evolution unusually close to observation. They allow change to be seen, not only inferred. The limit also reminds astronomy that stars are not allowed to occupy every state that simple diagrams might suggest. A map can show an empty region, but the emptiness has a reason. Some combinations of temperature and luminosity do not last because the physics removes them. The star reaches the edge, loses matter, and is redirected. What looks like a gap in a diagram is really the trace of instability acting over time. For the blue Hypergiant, this inability to cross is part of its self-ending nature. The star cannot remain hot and blue forever because the core is evolving. It cannot become cooler and extended at the same luminosity without risking severe mass loss. It cannot keep all its envelope because its own light is too effective at lifting gas away. Every route changes it. Every attempt to settle becomes another way of losing what it once was. The space around such a star slowly fills with the result. Rings, shells, arcs, dusty knots, ionized gas, and expanding lobes become the outer evidence of a path that could not be taken smoothly. The star stands near the top of the diagram, but its history is not a line drawn in ink. It is written in matter, drifting outward through darkness. The next part of the journey follows those shells more closely. Around some of these stars, the surrounding nebula is not only a beautiful cloud, it is a memory of eruptions, winds, and failed crossings, a record of how a star sheds its own body while trying to survive its own light. Around the most luminous, unstable stars, space is rarely empty. The star may appear as a single bright point in a telescope, but the region around it often tells a longer story than the point itself. Gas surrounds it. Dust may lie farther out. Shells expand in slow silence. Rings curve through the darkness. Arcs of ionized material mark places where one outflow has pressed into another. A blue Hypergiant does not pass through its short life cleanly. It leaves pieces of itself behind. These structures are called circumstellar nebulae because they belong to the space around the star rather than to the broader interstellar medium. They are not the same as the original cloud from which the star formed, though they may blend into it with time. Much of their material once belonged directly to the star. It was part of the outer envelope, held by gravity, warmed by radiation, shaped by pressure, and then released. The nebula is the star, displaced. This is why the shells around blue Hypergiants and luminous blue variables feel different from ordinary scenery. They are not only beautiful clouds lit by a bright source, they are records of loss. Each expanding layer marks a period when the star's wind was stronger, or its envelope became unstable, or an eruption lifted mass away faster than gravity could reclaim it. The star's history does not have to be guessed only from its present light. It can be read in the material drifting around it. Eta Carinae gives the most famous example. At the center lies one of the most luminous stellar systems in the Milky Way, still hidden and complicated, still pouring energy into its surroundings. Around it stretches the Homunculus Nebula, a pair of opposing lobes created during the great eruption of the 19th century. The shape is not random. It suggests direction, structure, and a release of material that was stronger along some axes than others. The star did not simply shed a mist. It expelled a shaped body into space. The homunculus is made of gas and dust moving outward from the central source. It glows by reflected starlight and by thermal radiation from dust warmed by the star. In visible images, it can look like two dusty lanterns joined at the center. In infrared light, warmer regions reveal themselves in another way, as if the nebula has a hidden temperature map beneath its visible form. It is one of the rare cases where a star's recent instability has left a structure large enough and near enough to study in detail. The scale is quiet but immense. Material thrown out in a human-recorded eruption now spans a region large enough that light itself needs time to cross it. The gas is still expanding. It has not settled into the galaxy. It still belongs, in a physical sense, to the event that made it. Eta Carinae survived the eruption, but the nebula remains as proof that survival did not mean stillness. The star continued only after giving away a large part of itself. A different kind of memory surrounds P Cygni. This star became suddenly visible to the naked eye in the early 17th century, then faded over time. Its eruption left traces in the surrounding material, and its light carries one of the most important signatures of stellar wind. The P Cygni profile, seen in spectral lines, shows both emission from outflowing gas and absorption from material moving toward the observer while leaving the star. It is a pattern made by escape. That spectral pattern is a reminder that not every shell needs to be seen as a picture. Some structures are read in light itself. A line in a spectrum may reveal gas moving outward. A shifted absorption feature may show the speed of the wind. A broad emission line may suggest density and turbulence. The star's surroundings become visible not only through shape, but through motion written into wavelength. Eta Carinae provides another layer of the same story. Around it lies a ring-shaped nebula, material expelled during earlier unstable phases. The ring does not form a perfect mathematical circle, because real stars do not shed matter into ideal emptiness. The wind meets older gas. The star may rotate. The surrounding medium may be uneven. Outflows collide, slow, brighten, and cool. The result is a shell with texture, a structure that preserves both the force of ejection and the resistance of the space it entered. In images, these nebulae can appear calm. The human eye sees color and shape, not velocity. A shell may look almost suspended, as if it has always been there. But it is moving. It is expanding away from the star, often at speeds that would cross continents in moments if such motion belonged to Earth. In space, over such distances, the expansion becomes graceful. The motion is fast in physics and slow in the sky. The shells also reveal that mass loss is not always smooth. A steady wind would create a more continuous distribution of material, thinning gradually with distance. Many observed nebulae show layers, knots, arcs, and uneven densities. That structure suggests episodes. The star did not lose matter in one unchanging flow. It changed its rate. It brightened and faded. Its envelope swelled and relaxed. Its wind thickened, then thinned again. The nebula keeps the rhythm after the star has moved on. Some shells are enriched with material processed inside the star. Nitrogen may be enhanced where hydrogen burning through the carbon-nitrogen-oxygen cycle has altered the composition. Helium may become more visible as outer layers are stripped away. Carbon and oxygen can appear later depending on how deep the mixing and mass loss have gone. The nebula therefore tells not only that matter was lost, but something about where that matter came from within the star. The outer cloud carries chemical clues from the inner life. This makes the space around a blue hypergiant a kind of archive. The innermost wind shows what the star is doing now. A shell farther out may record an eruption centuries or thousands of years earlier. A still wider structure may show older mass loss from a previous phase. Each layer is moving at its own speed, with its own density and chemical signature. Together they form a timeline made of gas. The archive is not always easy to read. Shells can collide with one another. A faster wind from a later phase may catch a slower shell from an earlier phase, compressing it and making it glow. Dust can hide parts of the structure. The surrounding star-forming region can add unrelated gas along the same line of sight. A companion star, if present, can shape outflow into spirals, disks, or bipolar forms. The record is physical, but not simple. Still, the presence of these nebulae changes how the star is understood. A blue hypergiant is not only defined by the light reaching observers in the present moment, it is defined by what surrounds it. A star that has already expelled several solar masses has a different future from one that has not. The material outside alters later observations, later winds, and eventually the final explosion if the core collapses. The past remains near enough to matter. When a massive star finally dies, it does not explode into a clean vacuum. It explodes into its own earlier life. The blast wave meets wind-shaped gas, older shells, dust, and enriched material already traveling outward. That collision can turn motion into light, making some supernovae brighter and longer lasting than they would have been otherwise. The nebula is not only a remnant of what came before, it can become part of what happens at the end. This connection gives the shells a quiet importance. They are beautiful, but they are not passive. They store mass close to the star. They create density structures through which future shock waves must travel. They contain elements that will be mixed again when the final event pushes through them. The star's earlier instability prepares the stage for its death. There is also a softer way to see them. The shells around a restless star are like rings in a tree, except they expand outward instead of remaining locked in wood. They show seasons of loss, periods of calm, and sudden changes in the life of an object too hot and too bright to last. The comparison is imperfect, but the feeling is useful. A blue hypergiant has no solid trunk, no bark, no quiet growth, yet it leaves rings all the same. Far from the central glare, the outermost gas begins to blend with the surrounding medium. What once belonged to one star becomes harder to separate from the galaxy. Dust cools. Ionized gas recombines. Winds from neighboring stars press against the fading shell. Over long spans, the material will lose its identity as a personal nebula and become part of the wider interstellar cloud. The star's lost surface will return to the raw mixture from which other stars may form. For a while, though, the identity remains. A telescope can still see the shape. Spectra can still measure the motion. Infrared instruments can still detect the dust. The star still stands at the center, changed by the loss and surrounded by its evidence. In that arrangement, the blue hypergiant becomes easier to understand. It is not a single body ending at a surface. It is a star and a moving memory around it, a central fire with its own past drifting outward in layers. The next part of the journey follows that drifting matter into a dimmer kind of visibility. Some of the most luminous stars may be partly hidden by the very dust and gas they have expelled, so that ordinary light tells only part of the truth. To see them clearly, astronomy must often look beyond the visible into the warmer glow of infrared light. Visible light tells only part of the story around a blue hypergiant. The star may be bright enough to reshape a nebula, bright enough to ionize gas across light years, bright enough to press its own surface outward, and still be partly hidden from view. The hiding does not come from some distant cloud between Earth and the star. It can come from the star itself. The same winds and eruptions that reveal its instability can build a veil around it. Dust is the quietest part of that veil. It forms in cooler regions of expelled gas, far enough from the central heat for atoms and molecules to begin gathering into tiny grains. Close to the star, the radiation is too harsh for dust to survive. Farther out, in the shadowed and cooling parts of the ejecta, small grains can persist. They are tiny, but in great numbers they become effective at blocking visible and ultraviolet light. The star shines. The dust receives that light. Some of it is absorbed before it can travel freely into space. This absorption changes how the star appears. A blue hypergiant may pour most of its energy into ultraviolet and visible wavelengths, but a dusty envelope can intercept part of that radiation. The dust warms. Warm dust does not remain dark. It releases the absorbed energy again at longer wavelengths, especially in infrared light. To an optical telescope, the star may seem dimmed, reddened, or partly buried. To an infrared instrument, the surrounding dust begins to glow. The effect is similar to seeing a lantern through fog, except the fog has been made by the lantern itself. The light that cannot come directly through the veil is transformed. It leaves in another color, outside the range of the human eye. Infrared astronomy follows that transformed light. It looks for warmth, for dust, for the hidden structure of matter around stars whose visible surfaces may be obscured. This is especially important for the most unstable luminous stars. A blue hypergiant that has lost much of its outer material may not sit in clear space. It may be wrapped in shells, knots, and dusty ejecta from earlier phases. The central star can be so bright that it heats this material from within, while the material itself blocks a direct view of the source. The star becomes both lamp and prisoner, lighting the walls of its own enclosure. Some candidates for the blue hypergiant or luminous blue variable state are difficult to study for this reason. They are not always clean blue points against a simple field of stars. They may be embedded in dense circumstellar material. Their visible light may be weakened by extinction, the dimming caused when dust absorbs and scatters light along the path to the observer. Their true luminosity has to be reconstructed by combining visible, infrared, and sometimes radio observations, along with careful estimates of distance and dust. This makes the act of measuring such a star more delicate than it might seem. Brightness on the sky is not the same as luminosity. A star can look faint because it is distant, or because dust lies in front of it, or because much of its energy is emerging in wavelengths not seen by ordinary eyes. To understand it, astronomers must gather the light across many bands and ask where the missing energy has gone. Often, around dusty hypergiants, the answer is that the light has been absorbed and re-emitted by the star's own surroundings. Infrared light is well suited to this search. Longer wavelengths pass through dust more easily than visible light, and warm dust itself radiates strongly there. Instruments that observe in infrared can reveal shells and envelopes that optical images miss. They can show where expelled material is cooling. They can trace the shape of dust formed from earlier eruptions around some massive stars. The infrared view changes the entire sense of the object. What looked like a dim or confusing source becomes a central star surrounded by its own lost mass. AFGL 2298 is often discussed in this context as a heavily obscured luminous blue variable candidate. It is bright in infrared light while being difficult to study in visible wavelengths because of the dust and material along the line of sight. Objects like this remind astronomy that the known population of blue hypergiants and related stars may be incomplete. Some may be hidden in crowded star-forming regions. Some may be wrapped in their own ejecta. Some may have been catalogued first as infrared sources before their true nature became clearer. The Milky Way itself makes the search harder. The disk of the galaxy is full of dust, especially toward its inner regions, where many massive stars are born. Young clusters can sit behind thick lanes of interstellar material. A blue hypergiant in such a place may be luminous enough to affect its local cloud and still remain difficult to see from Earth in visible light. Infrared surveys have therefore been essential for finding and studying massive stars buried in the galactic plane. There is a quiet irony here. The stars being sought are among the brightest individual stars known, yet some are hidden because brightness alone does not guarantee visibility. Light must pass through matter, and matter changes light. A star can be intrinsically enormous in output and still appear muted if the path is filled with dust. The universe does not present its brightest objects in a simple order. Sometimes the strongest light arrives indirectly. Dust also preserves information. Its temperature, distribution, and composition can help reveal the history of mass loss. Warmer dust closer to the star may trace more recent ejections or regions still heated strongly by the central source. Cooler dust farther out may belong to older material, expanding away for longer. A shell bright in infrared may mark an eruption that is no longer obvious in visible light. The dust becomes another archive. Less sharp than a spectrum in some ways, but rich in memory. The shape of the dust can also suggest how the mass left the star. A nearly spherical shell may point to a broad outflow. A ring or disk may suggest the influence of rotation or a companion. Bipolar lobes may reveal that material escaped more easily along certain directions. Clumps may show that the ejection was uneven, or that the wind became unstable as it moved outward. In the infrared, these shapes can appear as soft structures of warmth spread around a central source that may itself be hidden. The companion question is especially important. Many massive stars are not alone. A nearby star can disturb the envelope, exchange mass, spin up the primary star, or carve structure into the outflow. In a dusty system, a companion may help explain why material forms a disk, spiral, or bipolar nebula, rather than a simple shell. The dust then carries not only the memory of mass loss, but the memory of gravitational interaction. Infrared observations do not remove every uncertainty. Distance can still be difficult. Dust properties must be modeled. The amount of light absorbed and re-emitted depends on grain size, temperature, density, and geometry. A star surrounded by dust can be misread if too much of the energy is hidden, or if nearby sources contaminate the measurement. Massive star-forming regions are crowded, and the glow of one object can blend with another. The hidden star requires patience, yet the infrared view is one of the gentlest and most revealing ways to approach these objects. Visible light shows the hot surface and the ionized gas. Spectra show winds and chemical signatures. Infrared light shows what has been warmed after being lost. It follows the star's energy into the material around it. It traces the way a blue hypergiant fills its surroundings with the evidence of its own instability. The image is quiet. A star too luminous to keep its outer layers sends them away. The expelled matter cools. Dust forms in the moving gas. The dust absorbs the star's light and glows softly in infrared, turning the star's violence into a hidden warmth. From a great distance, the scene may not look violent at all. It may look like a dim red source, a blurred patch, a glow in the galactic plane. Inside it, a star is still shining with a force that would overwhelm any nearby world. This hiddenness changes the meaning of rarity. Blue hypergiants are truly rare because massive stars are rare and the phase is brief. But the number known may also be shaped by how difficult they are to see. Some have likely been missed because they are far away, dust-reddened, crowded among other massive stars, or wrapped in their own ejecta. The census of the most luminous unstable stars is not only a count of what exists, it is also a count of what instruments can reach. As instruments improve, the hidden population becomes less silent. Infrared surveys map warm dust across the galaxy. Space telescopes remove the blurring and absorption caused by Earth's atmosphere. Spectroscopy separates the light into signatures of temperature, velocity, and composition. Each method opens another layer of the veil. The blue hypergiant remains distant, but it becomes less alone in the dark. This matters because the dust around such a star is not a minor detail. It is mass that has already been removed from the star. It is part of the circumstellar environment into which later winds will move and into which a final explosion may one day expand. It affects how the star is measured now and how it will appear at death. The veil is also a stage. Behind that veil, the star continues toward a more stripped state. Each wind and eruption removes part of the hydrogen-rich envelope. Each lost layer brings the deeper, hotter regions closer to the surface. Eventually, in many massive stars, the blue hypergiant or luminous blue variable phase gives way to something more exposed, a star whose outer clothing has been mostly removed, leaving the fierce core beneath to shine through. Beneath the glowing wind and the dusty veil, the blue hypergiant is changing from the inside as well as from the outside. Its surface may swell, cool, brighten, or hide behind material it has already lost. But deep below those moving layers, the core follows another clock. That clock is faster than the surface seems to suggest. It is not measured by the quiet patience of the sun. It is measured by fuel disappearing in stages that grow shorter as the star approaches its end. A massive star begins with hydrogen burning in its core, as all ordinary stars do. In a blue hypergiant, that hydrogen burning is intense because the core is hot and highly compressed. The carbon-nitrogen-oxygen cycle carries much of the work, turning hydrogen into helium with a speed that belongs to high-mass stars. For a while, this process supports the core against gravity. Energy flows outward. The envelope shines. The star holds its great shape, even while the outer layers are already being pushed away by radiation. But core hydrogen cannot last. When the central hydrogen is mostly gone, the core changes. Without the same supply of fusion pressure from hydrogen burning, it contracts under gravity. Contraction heats it. That heat allows the next fuel to burn. Helium begins to fuse into carbon and oxygen, and the star enters a deeper stage of its life. The outside may still look blue, or it may pass through a luminous variable phase, but the center has already moved on. This is one of the quiet difficulties in understanding massive stars. The surface does not always reveal the exact state of the core. A star may look like a blue hypergiant, while its interior has already advanced beyond the first long stage. It may be losing mass from above, while the center builds heavier elements below. The outer and inner stories are connected, but they do not move at the same pace. As helium burning continues, the outer envelope is still being stripped. Winds carry hydrogen-rich gas into space. Eruptions can remove still more. Binary interaction, if a companion star is close enough, may pull material away or alter the way the envelope is held. Every lost layer exposes material that was once deeper. The star becomes less like its original form and more like the remnant of its own earlier mass. If enough of the hydrogen-rich envelope is removed, the star can enter the Wolf-Rayet state. A Wolf-Rayet star is extremely hot, luminous, and stripped. Its surface no longer shows the same outer material that once covered the star. Instead, products of nuclear processing appear closer to the surface. Strong emission lines reveal powerful winds. The star has not become calm. It has become exposed. The transition is not a simple shedding of clothing in one moment. It is gradual, uneven, and shaped by many forces. Radiation-driven winds may remove mass steadily. Eruptions may tear away larger portions. A companion may strip the envelope faster than wind alone. Rotation may mix material upward from deeper layers. The path from blue hypergiant to Wolf-Rayet star can be direct in some cases and complicated in others. The categories are useful, But the star itself is a moving object, not a fixed label. A stripped star can be hotter at the surface because deeper layers are now visible. The outer hydrogen blanket, once thick and extended, has been reduced or removed. What remains is closer to the core, denser, hotter, and chemically changed. The wind continues, often at very high speed, carrying away material enriched by nuclear burning. Space around the star receives not just ordinary surface gas, but matter that has been altered by the star's interior. This is how massive stars enrich galaxies even before they die. Carbon, nitrogen, oxygen, helium, and other products can be lifted outward by mixing and then lost through wind. The star does not need to wait for a supernova to return processed material to space. Its life is already a form of chemical release. The wind becomes a slow distribution of what the core and inner layers have made. Below that wind, the core keeps moving through its sequence. After helium, carbon burning begins when the core has contracted and heated again. This stage is shorter than helium burning. Later, neon burning follows, then oxygen, then silicon. The names are simple, but the pace changes sharply. Each new fuel requires higher temperature. Each new stage releases less useful energy compared with what the star needs to hold itself up. The core works harder for shorter rewards. Hydrogen burning may last millions of years in the most massive stars. Helium burning may last hundreds of thousands of years or less. Carbon burning may last only thousands of years. Neon burning may be measured in years or less. Oxygen burning can be shorter still. Silicon burning, the final major stage before iron, may last only days. The star that once shone for millions of years begins to change internally on timescales that feel almost sudden beside its earlier life. This shortening happens because fusion is approaching a limit. Lighter elements can release energy when their nuclei combine, and that energy supports the star against collapse. But the chain cannot continue forever. As the core builds heavier nuclei, it moves toward iron. Iron sits near the most tightly bound state of normal nuclear matter. Fusing iron does not release useful energy for the star, it costs energy. When the center becomes iron-rich, the old support system is near its end. While the core races toward this condition, the stripped outer star may still be losing mass. The surface can show the marks of a Wolf-Rayet phase. The wind may become fast and dense. The surrounding shells from earlier blue Hypergiant or luminous blue variable phases may keep drifting outward. The star is now layered in time. Old hydrogen-rich ejecta farther away, newer stripped winds closer in, and an interior that is preparing for collapse. The geometry of that material can matter later. If the star dies in a core collapse supernova, the blast wave will not move through empty space. It may first pass through a wind shaped by the Wolf-Rayet phase, then strike older shells from the blue Hypergiant stage, then meet even older material lost during eruptions. Each layer can change the light of the final event. The star's life builds the environment of its death. The stripped core also changes the possible remnant. A star that loses much of its envelope may explode differently from one that keeps it. The type of supernova seen from far away depends partly on which elements remain in the outer layers. If hydrogen is mostly gone, the explosion may lack the strong hydrogen features seen in other core collapse events. If helium is also reduced, the spectrum changes again. The final light carries the history of what was removed. This is why mass loss is not a side note. It decides how much of the star reaches the end, what surrounds the star at that end, what elements are visible in the explosion, and what compact object may remain. A blue Hypergiant born with enormous mass may not die with that same mass. It may spend much of its brief life giving itself away, through wind, outburst, and stripping, until the object that collapses is far smaller than the star that formed. There is a quiet reversal in this. The star begins as something excessive, a body with too much mass for a long, calm life. Then its own brightness removes that mass. The larger birth produces the stronger light. The stronger light produces the stronger loss. The star approaches death not simply as a giant, but as something carved down by its own power. A Wolf-Rayet star can therefore be seen as a later face of the same story. It is not the opposite of the blue Hypergiant. It is one possible result. The blue Hypergiant is extended, luminous, unstable, and often wrapped in lost material. The Wolf-Rayet star is hotter, more exposed, and still losing mass through a fierce wind. One state leads into the other when the envelope has been removed enough for the deeper star to show through. In some cases, the transition may not be fully completed before the end comes. The core may collapse while the star still carries part of its envelope. In others, binary stripping may remove the envelope earlier. In still others, lower metallicity may allow the star to keep more of its mass, changing the final remnant. The details vary, and current models continue to adjust as observations improve. The broad motion remains. The most massive stars are being uncovered while their cores are being exhausted. The image at this stage is not of one simple sphere. It is of a central furnace, nearly finished with its sequence of fuels, surrounded by layers that have been peeled, stirred, and lost. Around the star, older shells drift outward. Closer in, a faster wind flows from exposed hot material. At the center, the core approaches iron, where fusion can no longer provide the same answer to gravity. The blue Hypergiant's brightness once made it seem almost unlimited, but the stripped core beneath shows the opposite. The star has limits everywhere. Its envelope cannot resist the pressure of light forever. Its fuel cannot continue releasing energy forever. Its mass cannot remain attached forever. Layer by layer, reaction by reaction, it moves toward the moment when the inner support fails and the final shape of the star must be decided. At the center of the stripped star, the last support begins to fail. For millions of years, fusion has answered gravity with heat. Hydrogen answered first, then helium, then heavier fuels in shorter and shorter stages, each one burning under greater pressure, each one lasting for less time than the stage before it. At the end of that sequence, the core reaches iron. There, the long exchange changes. Iron does not give the star usable energy when it fuses. It takes energy away. The core has no gentle way forward. Gravity presses inward, and the old source of outward pressure weakens. The material at the center contracts. The contraction becomes collapse. In the final moments of an iron core, the inward fall is not slow, stellar aging anymore. It is a physical failure moving through the center of the star with a speed that belongs to a different kind of event. The core, once broad enough to be imagined on a planetary scale, is crushed into nuclear density. Electrons and protons are forced together to make neutrons. Neutrinos are released in immense numbers, carrying away most of the energy of the collapse. A neutron star may form if the remaining core can stop falling. If the core is too heavy, even neutron pressure cannot hold it, and the collapse can continue into a black hole. The outer layers, still above the collapsing center, receive the consequences from below. A shock wave is born, starlight, is revived by energy flowing through the collapsing core, and moves outward through the star. In many massive stars, this becomes a core collapse supernova. The shock crosses the remaining layers, heating and accelerating them until the star is torn open. Material that once formed the envelope is thrown into space. Elements forged during the star's life are released. New elements are made in the explosion and in the expanding debris. For a short time, the dying star can become one of the brightest objects in its galaxy. A blue hypergiant does not usually die in isolation. It has spent its life preparing the space around it. Winds have filled the surrounding region with gas. Eruptions have thrown shells outward. Dust has formed in cooled ejecta. Older material may lie farther away, while newer, faster winds move closer to the star. The final explosion, if it comes as a supernova, expands into this layered environment. The star meets its own past. That meeting can change the light of the death. When the supernova blast wave strikes dense circumstellar material, some of the motion becomes radiation. Gas is compressed and heated. Shock fronts form where the fast debris catches slower shells. The event can shine more brightly and for longer than it would in cleaner space. In such cases, the luminosity seen from far away is not only the light of collapse, it is also the light of collision between the end of the star and the matter it lost before the end arrived. This is one reason some of the most luminous stellar explosions are linked to very massive, unstable progenitors. A star that has thrown away several solar masses shortly before collapse can create a dense field of material close enough for the explosion to strike. The final brightness then depends on two histories at once: the inner history of the core and the outer history of mass loss. The death is shaped by the life. Not every blue hypergiant follows the same ending. The most massive stars lie in a region where models are still being refined, and the exact outcome depends on birth mass, metallicity, rotation, binary interaction, and how much mass has been removed before collapse. Some may end as ordinary core collapse supernovae in the broad sense. Some may produce unusually bright interacting explosions because of dense circumstellar shells. Some may collapse with surprisingly little visible light if too much of the star falls inward. In the most massive cores, another possibility appears. If the core becomes hot enough, energetic photons can transform into pairs of particles and antiparticles, electrons and positrons. This process removes pressure from the radiation field that had been helping support the core. The loss of pressure triggers contraction. The contraction heats the core further. In certain mass ranges, oxygen burning can ignite explosively and disrupt the entire star. This is called a pair instability supernova. A pair instability supernova is different from ordinary core collapse. It can leave no neutron star and no black hole behind if the disruption is complete. The whole star is unbound. The core's nuclear burning becomes powerful enough to tear the star apart. Such an ending is expected only under certain conditions, especially when the final core mass remains high enough. Low metallicity can help make that possible, because weaker winds allow the star to keep more mass until late in life. Here again, the chemistry of the birth cloud reaches all the way to the last moment. There is also the opposite kind of ending, quieter in light and deeper in gravity. If the final core is heavy enough, collapse may proceed directly into a black hole. The outer layers may not be ejected with the force of a bright supernova, or the explosion may fail after beginning. Some material may fall back. The star can disappear more softly than expected. Not because the event is gentle at the center, but because the energy does not escape in a way that makes a long, bright display. A massive star may end by making a dark object and leaving only a faint or brief sign behind. This possibility gives blue hypergiants a strange range of endings. A star that once poured out millions of times the sun's light may die in an event bright enough to announce itself across a galaxy. Another, depending on its final structure, may vanish into a black hole with far less visible display. The brightest life does not guarantee the brightest death. The final outcome depends on what remains after the winds. Eruptions, stripping, and core burning have finished their work. Rotation can alter the path. A rapidly rotating massive star can mix material between layers, feed fresh fuel into the core, and change the way mass is lost from the surface. Rotation can also help shape the final collapse, especially if the core keeps enough angular momentum. In rare cases, a collapsing massive star may produce narrow jets and an unusually energetic explosion. These events are not the standard fate of every blue hypergiant, but they belong to the wider family of possible endings for the most massive stars. Binary companions complicate the story further. Many massive stars are born in pairs or groups. A companion can remove the envelope through mass transfer. It can add angular momentum. It can merge with the primary star. It can shape the surrounding gas into disks, spirals, or bipolar forms. What looks like the fate of one star may actually be the result of two stars exchanging matter and gravity over millions of years. The blue hypergiant state may be only one visible chapter in a shared evolution. Because of these complications, the death of blue hypergiants remains an active field of research. Observations give pieces of the answer. Spectra of unstable stars, infrared shells around hidden sources, supernova light curves shaped by circumstellar interaction, gravitational wave detections of heavy black holes, and archival images showing stars before they exploded or faded. Each piece narrows the possibilities, but no single path explains every object. The most luminous stars still keep some of their endings partly hidden. What is certain is that their lives change the galaxy. Long before death, their radiation carves clouds, and their winds return gas to space. During eruptions, they throw out material enriched by internal nuclear processes. At death, if an explosion follows, heavier elements are scattered farther and mixed more violently into the interstellar medium. Oxygen, carbon, silicon, iron, and many other elements move outward from the place where the star once burned. The material does not stay as a monument. It joins the wider dark. Over time, the debris slows. It mingles with older gas. Shock waves fade, dust grains survive, or are broken and remade. The clear identity of the star's ejector softens into the surrounding medium. Later, another molecular cloud may gather. Gravity may draw that enriched gas inward again. New stars may form from it. Around some of those stars, disks may appear. In those disks, planets may collect from grains that include material once lifted from the envelope or core of a dying giant. This is the final gift of a blue hypergiant. Its life is short, and its structure cannot last, but its matter does not end with the star. The elements it releases become part of the next cycle of formation. The instability that made the star lose itself also helped move heavy material into space. The death that may look like destruction from far away is also a redistribution. The brightest stars are therefore not only brief lights in young clusters, they are engines of change. They open cavities in gas clouds. They seed their surroundings with processed matter. They prepare their own circumstellar stages, then collapse, explode, or fall inward according to the hidden balance left at the end. Their lives are too intense to remain stable, but that same intensity makes them part of the galaxy's renewal. Somewhere in the dark, a shell from such a star is still expanding. Somewhere else, dust warmed by a hidden luminous source is glowing in infrared light. Farther away, gas enriched by an older explosion is cooling inside a cloud that has not yet formed its stars. The blue hypergiant that gave it away may be gone, or stripped, or collapsed into darkness, but the matter continues outward, quiet now, carrying the memory of blue light into the next long sleep of the cosmos. The light has moved far now, beyond the young clusters and the blue stars that burn too quickly to remain. Behind it, shells of gas continue their slow outward drift. Dust cools in the dark. Old radiation fades into longer wavelengths, softer and softer, until even the memory of the star becomes part of the wide background of space. Nothing needs to be followed any further. The nebula can keep expanding without being watched. The hidden dust can keep its warmth. The stripped core, the final collapse, the scattered elements, all of it can settle back into the silence, where stars spend most of their lives unseen. The universe does not hurry after its brightest fires are gone. It lets the material travel. It lets the clouds gather. It lets darkness hold what light has released. Far away, somewhere beyond the reach of the eye, a blue star may still be shining inside a young cloud. Another may already be wrapped in its own dust. Another may have ended long ago, leaving only a faint trace mixed into the gas between stars. They do not need names now. They can become points of distant light again, then mist, then memory, then nothing more than matter, waiting in the cold. The room is closer than the stars. The weight of the body is here. The breath is here. The night around the room is small compared with interstellar dark, but it is enough. Let the last image be simple. A quiet field of stars, a fading blue glow, and a thin shell of gas moving outward so slowly it seems almost still. The journey can end there, in that slow motion, with the universe continuing on without sound.